Hello, Hamza. Hamza, are you getting my voice? Hello. Are you getting my voice? Yeah. Okay. So today we will discuss. Today we will discuss the stopping potential and the photocurrent and the stopping voltage. So uh, this is a this is metal plate. This is also a metal plate, and this is a vacuum chamber. Inside this chamber, there are no particles, and this is metal plate. These two metal plates are connected with a battery and a rheostat system. Battery and a rheostat system. Battery is a source of energy, and rheostat is a variable resistance. With the help of the rheostat, we can change the resistance. Okay. So this is the metal plate. This is the metal plate. Suppose on this metal plate, radiations are incident. These are the radiations. Photons. So these radiations are incident on the metal plate. So what will happen? This metal have the free electrons on the surface. So when this radiation will fall on the surface of the metal plate, electrons are emitted. Those electrons are known as photoelectrons. So basically electrons are emitted. So this metal plate is known as collector, emitter, because this is emitting the electron, and cathode will give this metal plate is known as cathode or emitter. This metal plate is known as collector or anode. Anode or collector. So what will happen? Electrons are emitted, and electron will move from cathode to anode. Electrons will move from cathode to anode. Okay. So electrons are moving from cathode to anode. So cathode we will say C, and anode to anode we will denote with A. C for cathode, A for anode. Now just a minute, Hamza. So these electrons are moving from cathode to anode, means motion of the electron, motion of these electrons, and these electrons are photoelectrons. So electrons will move from here to here to here at anode, and finally electron will be move like this, electrons, and like this and like this. Okay, so due to the motion of these electrons, and these are photoelectrons, so we can say due to the motion of these photoelectrons there will be a current. That current is known as the photocurrent. That current is known as the photocurrent. You can see here photocurrent. The current due to photoelectrons emitted by cathode is called photocurrent. Now here electrons, here are more number of electrons, means in this small space large number of electrons are there, because electrons are emitted from this plate. Okay, and here the electrons are there in this region the electrons are there. So here are the more number of electrons in less space. So what will happen, the motion of the electron from cathode to anode will be restricted, and due to that there will be less photocurrent. There will be less photocurrent, and the collection of these electrons here is known as the space charge, because these electrons are in space. So to solve the problem of space charge, we will give positive potential to this plate. If we will give positive potential to this plate, so the electrons are attracted towards the anode and the problem of space charge will be solved. So you can see here space charge, the negative charge in the region between cathode and anode due to large number of photoelectrons, due to which low photocurrent. What is the solution? Increase positive potential on anode. What will happen when you will increase the positive potential on anode? On increasing the positive potential on anode with respect to cathode, more and more electrons are attracted towards anode and photocurrent increases. So due to this positive potential, the electrons are attracted towards the anode and photocurrent will increase. But after a certain period of time, after a certain value of the positive potential, the photocurrent will become constant, because the number of photoelectrons emitted are not increasing. Number of photoelectrons emitted are not increasing. Okay. Number of photoelectrons emitted depending upon the intensity of radiation. Intensity of radiation is same. So on increasing the positive potential on anode with respect to cathode, more and more electrons are attracted towards anode and photocurrent increases until, see this statement, until it reaches to a saturation value. Photocurrent will reach to a saturation value. Why? Because all the electrons are attracted towards the anode. Now at cathode there are no more electrons, because all the emitted electrons are attracted towards anode. Now no more photocurrent will increase. Photocurrent will become constant. Okay. So this is the photocurrent, space charge, and solution of the space charge. And what will happen when you will increase the positive potential on the anode? Now instead of positive potential, suppose we are giving negative potential to the anode. To the anode we are giving negative potential. So here if there will be a negative potential, then electron will experience a force of repulsion. So due to that force of repulsion, the motion of the electron will be restricted. The motion of the electron will be restricted. More the potential on the anode you will increase, more the motion of the electron towards anode will restricted, and the photocurrent will decrease. At a certain value of the negative voltage, no electron now will reach to the anode due to the force of repulsion. In that condition, the photocurrent becomes zero, and that potential at which that negative potential at anode at which no electron, even the single electron, can reach to anode is known as the stopping potential. Applying negative potential on anode. If we apply negative potential on anode with respect to cathode, photoelectrons are repelled by anode and photocurrent will decrease. On further increasing negative potential on anode, a saturation arises when no electron can reach at anode. Because why no electron now reaching to anode? Because the negative potential becomes very large and the force of repulsion on the electron becomes very large. So as a saturation arises when no electron can reach at anode, A for anode, and photocurrent becomes zero. So stopping potential, you can define the minimum magnitude of negative potential on anode with respect to cathode, which can just stop the photocurrent, is called stopping potential or stopping voltage. Photocurrent will become zero when no electron will reach to anode, because photocurrent is due to the motion of the photoelectrons from cathode to anode. Now no electron is reaching to anode, so no photocurrent will be there. So if you will draw the graph of the photocurrent versus the anode potential, so the graph will be like this. I is the photocurrent, I is photocurrent, I is photocurrent, and this is anode potential. So graph will be like this. Now we will analyze this graph. Okay, this is 0. This is 0. Now see from here. This is the anode potential. If you will increase the anode potential in positive direction, if you will increase the positive potential on anode, means if you are moving on this graph in this direction, so what will happen? From here to here, from here to here, from this point to this point, you can say this point, you can say from A to B on the graph. What is happening? You can see photocurrent is increasing now. Photocurrent is increasing. Photocurrent I increasing. This upper this arrow is representing increasing, and after a certain period of time, the photocurrent will become constant. So you can write after B, photocurrent constant. Now we will increase the negative potential on anode. So now this is 0. Increasing negative potential means you are going this side. So what will happen when you will increase the negative potential on anode? The photocurrent will decrease now. So the photocurrent is decreasing, 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 and finally the photocurrent will become 0 at a particular potential, and that potential is known as the stopping potential. So from A to C, this suppose this point is C. A to C, photocurrent is decreasing, and at C, photocurrent will become 0. Okay. So this graph is just like this, exactly if you will draw. Now we will do derivation of stopping potential. Expression, we will find the expression for the stopping potential. So now see, this is cathode, this is anode. Electrons are emitted from cathode, and electrons are moving from cathode to anode. And on anode now you are increasing the negative potential. When you will increase the negative potential, the force of repulsion on electron will increase. Due to that, the motion of the electron from cathode to anode will decrease. So initially, you can take any electron, this electron. So this electron will have the kinetic energy. This electron will have the kinetic energy. So when the electron is moving like this, and there is a force of repulsion on the electron in this direction. The motion of the electron, or the velocity or speed of the electron, will decrease. Okay. Due to the force of repulsion. Okay. Suppose you have applied here the stopping potential. So what will happen at the stopping potential? The electron means no electron can reach to anode. It means that the electron which will have the maximum kinetic energy, that also will not reach to anode. That electron having the maximum kinetic energy also will not reach to anode. Okay. So we can write, while moving from cathode to anode, while moving from cathode to anode, electron has to do work against electrostatic force on the expense of its kinetic energy. Of its kinetic energy. At a stopping potential, even the fastest electron, even the electron having maximum kinetic energy will not reach to anode. reach to anode and photocurrent becomes 0. Okay, so you can say that the electron having the maximum kinetic energy maximum, and suppose there is an electron here, and that electron is having a maximum kinetic energy, and that is moving from cathode to anode, and due to the negative potential there is a force of repulsion on anode. So what the electron have to do in moving from cathode to anode? The electron have to do some work against the electrostatic force of repulsion. So the kinetic energy of the electron will decrease, or you can say in doing that work the kinetic energy will expand. So electron move and spending kinetic energy again and again. Spending means in moving from cathode to anode, what is happening? Electrons kinetic energy is spending. So spending. There is a time when the kinetic energy of the electron will become 0. Means total kinetic energy of the electron is spending in doing the work. Okay, so you can say the electron having the maximum kinetic energy, that kind maximum kinetic energy is spended in doing the work done. And we have the formula of the work done: charge into delta V, and delta V is what? V. So that will be Q into V naught. Delta V is V naught now, because this is V naught and this is a zero potential. I am assuming this is at zero potential. So electron is moving from zero potential to V naught. So work will be Q into V naught. So you can write maximum kinetic energy of electron is equal to work done is Q into V naught. So from here you can find V naught, that is equal to kinetic energy maximum multiplied by Q naught. So this formula or this expression of stopping potential you will get. Now maximum kinetic energy can be written as, we can simplify this. Maximum kinetic can be written as energy of photon minus work function of the metal, Einstein photoelectric equation. This is V naught, not Q naught. This is V naught. So it will be V naught. Now E can be written as Hc by lambda. So V naught can be written as Hc by lambda into V naught minus phi by V naught. Oh shit. Oh, this. Oh, just a minute. We have done one mistake. Charge on the electron is E. So work done will become E into V. So this will become E into V naught. So now you can say stopping potential equal to kinetic energy maximum divided by E. E is the charge on electron. Now we can simplify this expression. V naught is equal to kinetic energy maximum can be written as E minus phi, Einstein photoelectric equation, E. So V naught can be written as Hc by lambda E minus phi by E. Okay, so we can we can draw the graph between V naught and 1 by lambda. straight line graph with negative y-intercept, and this value of intercept will be c. C is the intercept, so 5 by e. And this value will be 1 by lambda naught. Lambda naught is the threshold wavelength. Okay, if this angle is theta, then slope of this graph can be given by tan theta, or from this equation also you can find slope. Slope is m, so this will be hc by e, because we are drawing the graph between v naught and 1 by lambda. So this will be the slope hc by e. hc by e. H is the Planck's constant, c is the speed of light, e is the charge on electron. Now, what will happen after this? What will happen when we will increase the intensity of incident radiation? If we will increase the intensity of incident radiation, number of photons will increase. If number of photons will increase, so more charge will flow from cathode to anode, means photocurrent will increase. Now, what about the stopping potential? You can see in this expression, stopping potential is depending upon E, energy of photon, and work function. Charge on electron is constant and work function is also constant. And this value is also constant because on increasing the intensity of radiation, number of photons will increase. Energy of each photon will remain same. So stopping potential will remain same. That is what I have written here. Stopping potential is given by hc by e lambda minus 5 by e. Stopping potential is depending upon lambda, means wavelength of the incident radiation, and the work function of the metal. So you can say on increasing the intensity of the light, the number of photoelectrons increases, which increases the number of ejected electron, means photoelectrons, and hence photocurrent increases because more number of photoelectrons, more will be the photocurrent, more will charge will flow from cathode to anode, so more will be the current. But energy of each photon still remains same, hence potential, stopping potential remain unaffected on changing the intensity of light. Okay, so this is a graph you can see. This is a graph between the photocurrent, anode potential. This is the graph between the photocurrent and anode potential for different intensity of radiation. So you can see here stopping potential is same, but the photocurrent is changing. Okay, if you will talk about this I3 is greater than I2 is greater than I1. Okay, but stopping potential is same because stopping potential is not depending upon the intensity. If you will increase the intensity, you can see the current, photocurrent is increasing. For this I1 intensity, the photocurrent is this, I2 intensity, the photocurrent is this, I3 intensity, here the photocurrent is this. So if you are increasing the intensity, the photocurrent is increasing, but stopping potential is same, no matter what the intensity of the light is. After this, we will discuss the wave nature of matter. Wave nature of matter. Now we know that what is photoelectric effect, and it was discovered in 1905. So photoelectric effect uh, gives the idea that light has the particle nature. Photoelectric effect proved that light or radiation has a particle nature. So light have the wave nature also, because light shows the interference, refraction, and polarization, and light shows the particle nature. How we can say that? Because of the photoelectric effect of light. There is one more effect, Compton effect, that can also be explained by considering the light as particle, black body radiation. After uh, that, there was a scientist named De Broglie. There was a scientist named De Broglie. So De Broglie said that nature has symmetry. If nature has symmetry means if light can be a particle, so matter can also be a wave. That is symmetry. So he gave his hypothesis that we will study. So nature has symmetry. So he said that matter can show the particle nature also, and matter can show the wave nature also. We know that matter is particle, but matter will also show, according to the De Broglie, wave nature. So now we will discuss the De Broglie hypothesis. So now what is De Broglie hypothesis? Every moving particle has a wave associated with it. Every moving particle has a wave associated with it, and these waves are known as matter waves. Okay, so these waves are known as matter waves. The waves associated with matter are matter waves. So he gave that wavelength of that wave, lambda of the wave, is given by h divided by p. And what is p? P is the momentum. What is momentum? If this is mass m moving with speed v, velocity v, so momentum p is given by mass into velocity. Okay, and lambda is the wavelength of matter wave. H is the Planck's constant. Wavelength of wave. P is the momentum. Now, for example, if there is a person moving with 10 meter per second having a mass of 100 kg, very fat person is there. So if the person is very fat and having a mass of 100 kg, so the person is moving, and person is what? Person is matter, and matter is moving. This person is what? This person is matter. And according to the De Broglie, if matter is moving, there will be a wave associated with that. And if there will be a wave associated with that, means there will be the wavelength. And that wavelength is given by h by p. So wavelength of the wave associated with this person is lambda, is h divided by p. P is the momentum. So h is 6.626 into 10 to the power minus 34 divided by momentum. Momentum is mass into velocity. Mass is 100 kg, velocity is 10 kg. So you will get lambda is equal to 6.626 into 10 to the power minus 27 angstrom. So you can see this value. This wavelength is very, very, very small. So the wavelength associated with large bodies are very, very small. So you can say very small, very, very small wavelength cannot be detected. So if this wavelength is very, very small, we cannot detect this wavelength, cannot be detected. Now, we will see for a small particle like electron. Suppose there is an electron and that electron have, we know like what the mass of the electron 9.1 into 10 to the power minus 31 kg, and this electron is moving with the speed of 10 to the power 6 meter per second. Now we will calculate the wavelength of the wave associated with motion of electron. So wavelength of the wave associated with matter given by de Broglie wavelength, that is h by p. What is h? 6.626 into 10 to the power minus 34 divided by momentum. Momentum is mass into velocity. Mass of electron is 9.1 into 10 to the power minus 31 into 10 to the power 6. So this value will be approximately equal to, you will get 7.33 into 10 to the power minus 10 meter. Means you can say it will be approximately equal to 7.33 angstrom. Now this wavelength is significant. This wavelength is significant. So we can say that if a smaller is the particle like uh, atomic particle like electron, very, very, very small particle is moving, then the wavelength of that the wavelength associated with the motion of that particle will be significant. Okay, this is lambda. This lambda is also known as de Broglie wavelength. Okay, this is also known as de Broglie wavelength. De Broglie wavelength. Okay, after this, we will drive the expression of de Broglie wavelength in terms of the kinetic energy. We'll drive the expression of de Broglie wavelength in terms of the kinetic energy. Suppose a mass m is moving with velocity v. So what will be the momentum of this mass? Mass into velocity. What will be the kinetic energy? K. K is the kinetic energy. Will be half mv square. Now from this you can find the v is equal to p by m, and this value of v you can put here. So the value of kinetic energy you will have half mv square means p square by m square. Now this m cancel with this. So kinetic energy will be p square by 2m. From here the momentum you will get under root of 2m into kinetic energy. Now if you want to find the de Broglie wavelength of this, then it will be lambda by p, h by p. So you will get lambda is equal to h upon under root of 2mk. Instead of p, you will put this value. It will be 2mk. So this will be the de Broglie wavelength in terms of the kinetic energy. K is the kinetic energy. M is the mass of the particle moving. H is the Planck's constant. Lambda is the de Broglie wavelength. Now, in terms of de Broglie wavelength, in terms of the uh, accelerating potential, de Broglie wavelength in terms of the accelerating potential. Suppose this is a charged particle, and this charged particle is moving from zero potential to the V potential. So if charged particle is moving from lower potential to higher potential, for the motion, this charged particle has to do some work, and to do that work, energy is required. Means the charged particle will spend its kinetic energy to do that work. Hmm? And what will be the work done in moving this charged particle from here to here? Q into delta V. And what is delta V? Delta V is the potential difference V minus 0, that is V. So it will be QV. Now the work is done on the expense of kinetic energy. I told you this charged particle is in motion. So in motion, what type of energy the charged particle will have? Kinetic energy. But to move the charged particle, for the motion of the charged particle from lower potential to higher potential, charged particle has to do some work, and that work will be at the expense of kinetic energy of the charged particle. Okay, so we can say we can say the work done is on the expense of kinetic energy. So you know that kinetic energy will be equal to work done, and that will be equal to QV. Okay, so kinetic energy will be equal to QV. And what is the wavelength? Lambda in terms of the kinetic energy, h upon under root 2mk. So in terms of, instead of this k, you can put QV. So lambda will be h upon under root 2m. Instead of k, we will put q into v. So this will be the formula. This is the wavelength in terms of the accelerating potential. Now for electron, suppose this is here is an electron, and this electron is moving from zero potential to potential V, and this data is there. Now if we will calculate the wavelength associated with the motion of this electron, so that wavelength will be given by h upon under root 2 mass of electron multiplied by 2m. It will be 2m QV. Charge on electron is E multiplied by potential V. So when you will calculate this, H is 6.626 into 10 to the power minus 34 under root of mass of electron is 9.1, 10 to the power minus 31, charge on electron 1.6 into 10 to the power minus 19. When you will find out this value will come out to be under root of 150 divided by V, and this value will be approximately equal to 12.27 divided by under root of V, and this is valid for electron only. Understanding, Hamza? Hamza, understanding? Hello, Hamza? Hamza, your voice is too slow. Actually, your voice is very, very slow. Okay, so take the screenshot and when you have you took
Sir,
a
is it clear
screenshot.
now?
Now it's clear. Now it's clear. So take the
Okay, sir.
screenshot. Screenshot.
Done.
Okay. Done.
Right, sir. 1 minute, can you go? Mhm. Done. Done. Done.
Okay.
Done.
Okay.
Done. 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 Done.
Okay.
Done.
Okay. So this is the question that we will solve now. This. Mm, mm, mm. The ratio between the de Broglie wavelengths associated with protons accelerated through a potential of 500 volt, accelerated through a potential of 512 volt, and alpha particles accelerated through a potential of x volt is found to be 1. Find the value of x. Very easy question. Proton is there. P for proton. Proton is accelerated to 0 to V potential difference. Okay. 0 to V potential difference. And alpha particle is there. And this alpha particle is accelerated from 0 to x volt potential difference. We have, and the ratio of wavelengths is 1. We have to find the value of x. So mass of proton, if m, then mass of alpha particle is 4 times of m. Okay. Charge on proton, if q, then charge on alpha particle is 2q. Okay. Now there is a relation between the wavelength and the accelerating potential. Lambda is equal to h upon under root of 2m qv. Okay. Now wavelength for proton is h upon under root of 2 into mass of proton is m, charge on proton is q, and this is v. And this wavelength is what? This wavelength is 512 volt given. So this will be h divided by under root of 2m qv. Suppose this is equation number 1. Now for alpha particle, same formula we will use. Lambda is equal to h upon under root 2m qv. So for alpha particle, h under root of 2 mass of alpha particle is 4 times of mass of proton, means 4m, charge 2q, and accelerated to x volt. So here we will put x. This is x, and this x we have to find. So suppose this is equation number, and this is equation number 2. Equation number 2. So they are saying the ratio of wavelength of. Okay, so what we should do now? Actually, we should remove this equation and consider this equation as equation number first. They are saying ratio of wavelength of proton and alpha particle is found to be 1. Ratio between de Broglie wavelength associated with proton and alpha particle is found to be 1. So means ratio of wavelength of proton divided by, ratio means 1 divided by 2. So ratio of wavelength of proton divided by ratio of wavelength of alpha particle is equal to 1. So you can say lambda p is equal to lambda alpha. Okay. So what is lambda p? Lambda p is this, h upon under root 2mqv. Lambda p is this, h upon under root of 2mqv. This is equal to lambda alpha. Lambda alpha is 4 to the 12 to the no, 4 to the 8 to the 16 mqx. Now h and h will be cancelled out, under root and under root will be removed. So you will have 2m qv, that is equal to 16m qx. Now mq will be cancelled out. What is the value of x? 2 by 16, 1 by 8. I think the answer is not correct. Just wait. What we have done, equal to 1, so it will be 2. The answer is right or answer is wrong? I think it should be right. It will be this 512 volt. If we will divide this, then we will get 1 or equal. Oh, sorry. Answer is right. Actually, this is 2. Here we have 2 into V. So this is 2, and V is the voltage of, means the proton is accelerated through a potential of 500 volt. This V is 512 volt. Okay, and this is 16x. Now x can be given by 2 into 512 divided by 16. Okay. So it will be 2, 8. Cancel this with 8. It will be 64. So the value of x you will get 64. This is your answer. In this way, you have to solve the question, you have to apply the formulas. One more question we will do. See this question. This is a good question. Two particles A and B of d Broglie wavelength lambda A and lambda B. There are two particles. This particle is A, this particle is B particle. This having a wavelength lambda A, particle having the wavelength lambda B. Okay. Combined to form a particle C. So both are combined and they form a particle C. Okay. And we have to find the wavelength of this particle C. So combined to form a particle, the process conserves the momentum. So during this process, the momentum is same. Okay. So now, before the collision, these particles will collide, na? These particles will combine. So before the combination of two particles, these two particles will be at rest. Okay, these two particles will be at rest. No. Suppose the initial velocity of this is VA and this initial velocity of this is VB and there is no particle number C. Okay, so momentum will be, so mass of the particle is suppose MA, mass of the particle will be MV. So from here we can find the momentum. So momentum of the A lambda A is h by momentum of A. So momentum of A is given by h by lambda A. Similarly, if you will find the momentum of particle B, it will be h by lambda B. Okay, so this is the initial momentum of the system, and finally they are combining. So if they are finally combining means finally they will become C. Finally they will become C. Okay, so lambda C means momentum of particle C we have to find. So before combining, momentum before combining is equal to the momentum after combining. Okay, momentum before combining is equal to momentum of the system after combining. So what is the initial momentum? This momentum plus this momentum, momentum of A plus momentum of B, that is equal to, finally both these becomes this C. So it will become momentum of C. Okay. So momentum of A plus momentum of B. So it will be H by lambda A plus H by lambda B. And this is equal to momentum of particle C. So now take H common. It will become 1 upon lambda A plus 1 upon lambda B will be the momentum of C. Now wavelength of C can be given by H by momentum of C. So it will become H divided by H by this 1 upon lambda A plus 1 upon lambda B. Now from here H and H will be cancel out. So you will have this value 1 upon, now you can write here lambda A plus lambda B and it will become lambda A lambda B. So this will be the value of wavelength of C. This is tricky question. Lambda A plus lambda B. Actually, in this question, what you have to do, there is no requirement of velocity. There is no requirement of mass. Okay. So this is particle A having the wavelength lambda A. So this from this lambda A, you can find the momentum of A initially. From this lambda B, you can find momentum of B initially. Finally, they are combining and becoming one. So final momentum will be the momentum of particle C. So you want to you can find the momentum of particle C because momentum is conserved. Momentum of particle C will be sum of the initial momentum. So you will get momentum of C is this, and you can find the wavelength. Okay, so take the screenshots. So these are the questions of board exam. Hamza, are you understanding? Are you understanding or not? Hello, Hamza. Hello, Hamza. Hamza, are you taking screenshots? Hello. Hello, Hamza. Hamza, are you there? Hello. Hello. Hello, Hamza. Please take the screenshots.
Sir,
Hamza, are you there in the meeting?
yes, sir.
Are you getting my voice?
Yes, sir.
Okay, so please take the screenshot.
Done, sir.
Okay, so do this. Taken?
Done.
Take this.
Done, sir. Done, sir.
Okay. So this chapter is completed now. After this, in the next class, uh, okay, Hamza, mm, on Friday, will you available on Friday? Because I want to take the extra class.
Sir, what, sir?
I'm saying that on Friday I want to take the extra class. Are you available on Friday?
No, sir, not on Friday.
Okay. So on any other day, means Saturday and Sunday?
Saturday, sir, Saturday I have my pre-boards have started.
Pre-boards started from
They already started, sir.
already started. So,
Yes.
okay.
My physics finished.
So how was the exam of physics?
Physics was all right. The long answers as followed. Yeah. This one, what do you say,
Mm-hmm.
numericals? Some of
Mm-hmm.
them I keep forgetting the formulas.
Yeah, okay. So, if you are forgetting the formulas, so in that case, na, what you have to do, so you know what you should do. You should practice. There is no other way to learn the formulas. Means to do more number of question is the solution. So when you will go for the final exam, so make sure that there should be the enough practice of the questions so that you can solve the final question in the final exam. Understanding na?
Yeah.
So
Yes, sir.
because in the class we have only talking about the our class. So we have only 3 hours in 1 week. So each and every question we cannot, each and every topic we can complete, but each and every question I cannot practice. Means I cannot uh, solve here each and every question. So I can only help you. Okay, I can only show you the path, but on the path you have to travel. You have to move on the path. I can only show you the path. So on path you have to move by yourself. And one more thing that be honest always, and uh, keep doing hard work, and definitely the result will be good. Okay.
Yes, sir.
Okay, so will you join the classes during the exams? Means during other exams?
Already joining.
Yeah, yeah,
Today,
of course. Yeah,
tomorrow
yeah.
is an exam. Yeah.
Tomorrow is your which exam?
Not tomorrow. Tomorrow is biology. I do not take biology, so I do not have. But on
Okay,
Saturday, I have chemistry.
you have chemistry. Okay, so prepare well, do your best, and uh, okay, take it easy. Your exams will be good if you have done the work during the year, during the whole year. If you have done the work, your exam will be definitely good. And be honest always, and uh, do your best. Try to do your best always. Whatever will be the result, that will be another thing. But do your best at the moment that you are doing something. Okay, Hamza. So we will meet in the next class now, and this chapter is finished. And in the next class, we will finish the chapter atom. Okay,
Yes,
and
sir.
in 3 and 4 classes, I will try to finish your syllabus. Okay, so that you can revise on time and you should get good marks in your final exam. Okay, Hamza, all the best for your exams. Okay.